Jai Hind. Myself Nidhi Singh, Assistant Professor in AKGEC Engineering College. Today we are going to discuss University paper solution of BW 101, that is Fundamentals of Electrical Engineering, and this for the session 2023-24 semester 1. So we have already discussed the section A in the previous lecture. So in today's lecture, this is the next part 2 lecture, in which we are going to discuss the section B questions. So these are the section B, and in this section there are total 5 questions are there, and out of these 5 questions you have to attempt only 3 questions. So you have a choice among these questions, and all questions carry 7 marks. So the first question, as you can see, it is calculate the current across 20 ohm resistor using nodal analysis in the following circuit. So in this circuit you have to use nodal analysis and you have to find current in this 20 ohm resistor. Then you can see question B, you have to calculate the form factor and peak factor for half wave rectified voltage signal. This question is from unit 2, and in this question you have to find the form factor and peak factor for the half wave rectified voltage signal. Then question number C, this is from unit 3, that is from the transformer. Here it is given that the 100 kVA single phase transformer, the iron loss is given and the copper losses are given, and you have to find the full load efficiency and the half load efficiency of this transformer. Then the question number D, it is from unit 4, that is from the machines, and here the question is describe the working principle and torque slip characteristics of 3-phase induction motor. So you have to write the working principle and you have to draw the torque slip characteristic of a 3-phase induction motor. Then the last question is discuss briefly the types of batteries and explain any one type of secondary battery with the necessary diagram. So this question is from the last unit, that is unit 5th, and here you have to discuss different types of batteries and you have to explain any one kind of secondary battery. So we will discuss all these questions one by one. So let's take the first question. So in this question you have to calculate the current across 20 ohm resistor using nodal analysis. So now what is the first step of nodal analysis? The first step of nodal analysis is to first find out the number of junction points, right? Junction points means there is a difference between node and junction point. Node means where 2 or more than 2 branches meet, but the junction point is where 3 or more than 3 branches meet. So in this circuit we have to identify number of, so here we have to identify the junction point. It means where 3 or more than 3 branches meet. So as in this circuit you can see that there are 2 junction points. So this is one junction point, right? So now this is junction A and this is second junction point, this is junction B, and this one is the third, which we call the reference point, which is at the potential 0, right? So total there are 3 junction points are there. So here now after identifying the junction point, the next step is to assume the node potential. So now I am assuming that the node potential here is VA and here it is VB. So VA and VB. Now I want to apply KCL at node A. So now you will write applying KCL at node A. So applying KCL at node A, what does this KCL means? KCL means the you can say that incoming current is equal to outgoing current, or you can say that algebraic sum of all the current at a junction point is equal to 0. So now as I am writing the I am applying the KCL at node A, so I will assume that my node A is at higher potential. So what does it mean? It means that all the currents are going outward from this node. I am assuming that this node is at higher potential. So I will write for this particular branch, I will write VA minus this 20 volt divided by this resistance 5. This is this branch current. So, this branch current, this then plus. Now, current in this branch you can write VA by 10, then plus VA minus VB. You can write VA minus VB by 10, and this is equal to 0 according to KCL, right? All these currents sum will be equal to 0. Now, we will apply KCL at node 8. So, applying KCL at node B. Now, I will apply KCL at node B. Now, I will assume that my node B is at higher potential. It means now all the currents is going outward from this node. So, now I will write for this branch. Now, as I am writing equation for this node and I am assuming that this node is at higher potential. So, now I will write VB minus VA by 10, VA minus VB by 10. Then now for this particular branch, I will write VB by 20, and now as this 4 ampere is entering in the node, right? This is entering in the node. So, we will write here minus 4 is equal to 0, right? As we are all the outward current, we are assuming positive sign. So, the current which will enter in the node, we will assume it for the negative sign. So, this will be minus 4 is equal to 0. Now, you will solve this equation and you can find the value of VA and VB. So, if you solve and you will get that this VA and VB, VA is equal to 20 volt and VB is equal to 40 volt. You will find that VA is 20 volt and VB is 40 volt. Now, the question is you have to find current in 20 ohm resistor, and this is a 20 ohm resistor. So, what is the current in this 20 ohm resistor? So, current in this 20 ohm resistor, I 20 ohm, this will be equal to, this will be VB by 20. So, VB is 40 by 20. So, this will be equal to 2 ampere. So, current in 20 ohm is 2 ampere. So, this is the required answer, right? So, now coming to the next question, this is calculate the form factor and peak factor of the half wave rectified voltage signal. So, this is the sine wave. So, after it this sine wave passes from the half wave rectifier, we know that we will get only the positive cycle and negative cycle will not be there, right? So, we have to find the form factor and peak factor. So, so before finding the form factor and peak factor, we should know the average value and the RMS value, because by using RMS and average value only we can find out the form factor and the peak factor, right? So, first we will find the average value. So, to find the average value, the formula is you have to integrate the cycle, you have to integrate you have to integrate this cycle for the whole period and you will divide it by the base length. So, what will be the base length is there. So, the one time period is for, if you see, the cycle is repeating from 0 to 2 pi. So, the full cycle is from 0 to 2 pi here. So, from 0 to pi you will get the sine wave, and from pi to 2 pi the value is equal to 0, right? So, now you can find V average as you will integrate from 0 to pi, because from pi to 2 pi the value is 0 and the base length will be 2 pi, right? The whole cycle is the 2 pi. So, V, the voltage, this is the voltage equation which is equal to Vm sin theta. So, you have to integrate this, and if you solve this you will get V average is equal to Vm by pi. So, this is the average value. Now, next you have to find the RMS value. So, to find out the RMS value, what you are going to do, you just need to square this term, right? You will square this term and you will put the under root. So, if you will get the RMS value. So, here you can see the RMS value under root and you will square the waveform. So, V, you know, V is equal to Vm sin theta. So, after solving this, if you will solve this and sin square theta, you can write minus 1 minus cos 2 theta by 2, and after solving you will get Vm by 2. right? So now you get the average value and the RMS value. So after getting the average value and the RMS value, now you can find the form factor and the peak factor. So form factor is VRMS by V average. So VRMS we find out Vm by 2 and V average is Vm by pi. So this will be equal to 1.57. Then peak factor is maximum value by the RMS value. So you will get it as 2. So this is the required answer, the form factor and the peak factor. Now the next question, a 100 kVA single phase transformer has iron loss of 600 watt and a copper loss of 1.5 kilowatt at full load current. Calculate the efficiency at full load, and the power factor is given 0.8 lagging, and the second you have to find efficiency at half load and the power factor is given unity, that is 1, power factor is 1 here. So now first we will write out the given values. So what are the given values here? The given values is it is given, the rating is given 100 kVA, or you can write 100 into 10 power 3 volt ampere, and iron loss is given, that is Pi, this is equal to 600 watt, 600 watt, and then copper loss is given 1.5 kilowatt, 1.5 into 10 power 3 watt, and you have to calculate full load efficiency and half load efficiency. So first we will find full load efficiency. So what is the formula for full load efficiency? Full load efficiency, this is equal to VA rating cos phi divided by VA rating cos phi plus iron loss plus copper loss into 100. So VA rating is given 100 into 10 power 3, and the power factor for this is given 0.8. So this is 0.8 divided by again VA rating, that is 100 into 10 power 3 into 0.8 plus iron loss is given 600 plus copper loss is given 1.5 into 10 power 3 into 100. So after solving this you will get the full load efficiency, right? So the full load efficiency is 97.44. 97.44%. You will get 97.44%, right? Then now to find half load efficiency. So this is how you will find the full load efficiency. Now next you have to find the half load efficiency. So now how to find the half load efficiency? So the second part, you have to find half load efficiency at half load, and this will be equal to, now you have to find it at half load. So N VA rating cos phi divided by N VA rating cos phi plus iron loss plus N square copper loss, this is full load copper loss into 100, right? And now what is N here? N is the fraction by which load is changed. So you can find N is equal to actual load divided by full load. So actual load is 50%, full load is 100%. So this will be equal to 0.2, right? This will be equal to 0.2. So, or you can say 1 by 2, right? This is 1 by 2. Sorry, 0.5. This will be equal to 0.5. Okay. So this is equal to 1 by 2. So now this will be equal to, so n will be 1 by 2, VA rating is, or you can write 0.5, this will be equal to 100 into 10 power 3, and for this unity power factor is given, that is by into 1 divided by 1 by 2, VA rating is 100 into 10 power 3 into 1 plus iron loss is given 600 and plus 1 by 2, or you can write a square, and copper loss is 1.5 into 10 power 3 into 100, and this is how you can find the half load frequency, right. So if you solve this, you will get 98.08. So if you solve for the full load, you will get answer 97.44, and half load you will get 98.08. So this is the required frequency at the particular load. Okay. Now describe the working principle and torque slip characteristic of three-phase induction motor. So we know that this three-phase induction motor works on the three-phase supply, and how this works here. In three-phase induction motor, we know that we have a stator and a rotor, right, and the stator is supplied with a three-phase supply. So when a three-phase stator winding is energized from the three-phase supply, you know that the rotating magnetic field is set up, which rotates around the stator at a synchronous speed ns. So when this rotating field passes through the air gap and cuts the rotor conductor, which are stationary. So due to the relative speed between the rotating flux and the stationary rotor, EMFs are induced in the rotor conductors, and since the rotor circuit is short circuited, current start flowing in the rotor conductor. So through this diagram also you can explain that this is a stator in which the three-phase supply is given, and because of that three-phase supply, the rotating magnetic field will be developed. Suppose here we have taken the direction as a clockwise. So here we have a stationary rotor conductor. So this magnetic field is rotating. So this will be cut by the stationary conductors here, and we know that when the because of this there will be a current will induced in this rotor conductor. So the current now this current carrying rotor conductors are placed in a magnetic field, and which is produced by the stator. So we know that the mechanical force will act on the rotor conductor. So the sum of the mechanical forces on all the rotor conductors produces a torque which tends to move the rotor in the same direction as the rotating field. So now the fact that rotor is urged to follow the stator field is because it can be explained with the Lenz's law, and according to this law, the direction of rotor current will be such that they tend to oppose the cause producing them, and the actual cause of this current is the relative motion, right. So the cause producing the rotor current is the relative speed between the rotating field and the stationary rotor conductors. So to reduce this relative speed, the rotor will start running in the same direction as that of the stator field, and it will try to catch it. So the rotor always slips behind the synchronous speed. It will never achieve the synchronous speed, because if it achieves the synchronous speed, the relative difference between the rotor and the this RMF will be 0, and if it will be 0, so there will be no induced current in this rotor conductor. So this current is getting induced, this EMF is getting induced in the rotor conductor because of the relative motion between the RMF and the rotor conductors. So this rotor always slips behind the synchronous speed, right. And the next part is the torque slip characteristic. So the torque slip characteristic, this is the torque slip characteristic. We can divide this into two regions, the low slip region and the high slip region. So in the low slip region, this S is very small, right, because the low slip region means the slip value is very small, and due to this the term Sx2 whole square is so small if you see in the torque equation. So this term will be so small as compared to the R2 square, and that can be neglected. So now here the torque is proportional to SR2 by R2 whole square, and we know the resistance is constant, right. So basically the torque is directly proportional to slip in this region. So in this low slip region, the torque is directly proportional to the slip, right? So, in this region, when the load increases, speed will decrease. The speed will decrease means there is an increase in the slip, and this increases the torque and which satisfies the load demand, right? So, as now the torque is directly proportional to S, so the nature of the graph is the straight line. Now, the next reason is the high slip reason. So, in this reason, slip is high, that is slip value is approaching to 1, and here we can assume that term this R2 square, this term R2 square is very small. So, we can neglect this term. So, now the torque is proportional to SR2 by SX2 whole square, which is inversely proportional to the slip here. So, in high slip region, we are getting relation that torque is inversely proportional to the slip. So, here you will get rectangular hyperbola. The nature of the graph is the rectangular hyperbola, and in this region, if the load increases, the speed decreases, and the speed decreases means there will be the increase in the slip. So, increase in the slip means torque will decrease. So, the same load will act as an extra load, and again the torque will again decreases and the motor will stop. So, motor never operates in this high slip region. This is called the unstable region. Motor always operates in the low slip region, and that is called the stable region. So, whenever this is a very important question, so whenever it comes, explain the torque slip characteristic of 3-phase induction motor, you have to explain the low slip region, you have to explain the high slip region, you have to draw this characteristic, and you will show that this low slip region is called stable region, the high slip region is called the unstable region. Then you have to locate all these points. This is the starting torque here, because when the motor starts, S is equal to 1, and here this is the maximum torque where S is equal to Sm, and this is the full load torque, which is always less than the maximum torque. So, you have to explain why the motor is why the high slip region is called unstable region. You are supposed to explain why the low slip region is called stable region, what the relation between torque and slip in low slip region, what is the relation between torque and slip in the high slip region, right? So, all these things you have to explain in this question. Now, the next one is discuss briefly the types of batteries and explain any one type of battery with the necessary diagram. So, we know that battery, these are the device which is consisting one or more electrical cell that convert chemical energy into electrical energy, right. So, we know that there are two kinds of batteries, the primary cell battery and the secondary cell, and we know that primary cell batteries, they are designed to be used for once, and once as they are discharged, we cannot recharge these types of batteries. So, some examples are like alkaline cell, aluminium air battery, atomic battery, Daniell cell or Ganwellic cell. These are the examples of these primary cell batteries. Now, the next type is the secondary battery. So, we know that secondary batteries, they can be recharged and they can be used many times. So, secondary batteries are those batteries which can be recharged after when it get discharged, and the example of such kinds of batteries are nickel cadmium battery, lead acid, nickel iron batteries, sodium ion, lithium ion, and these kinds of batteries are used in our mobile. We can recharge our mobile, your laptop, in your vehicles. So, these rechargeable secondary batteries are used in mobile phones and all. Then this is the example of the lithium ion battery. As the second part of the question, as you can see, it is written that explain any one type of secondary battery with the necessary diagram. So, here we have taken the example of lithium ion battery. So, the component of lithium ion battery are basically the cathode, which is a positive electrode made up of metal oxide. You can see here, this is the cathode, and the second part is the anode, which is a negative electrode made up of carbon, and we have a electrolyte. So, here we have a gel like electrolyte here, and the material of both the anode and cathode is such that they allow free flow of lithium ion through them. So, the main charge carrier is lithium ion in the lithium ion battery. So here in diagram you can see that here we have a lithium ion, this is the active material, then here we have a graphite, this is gel like electrode, and here also we have a lithium ion. So there are some advantages and disadvantages of this lithium ion batteries. So advantages are high energy and high power from power cell, high capacity and low internal resistance, and easy to charge and short charging time. Then self discharge is less than half of the nickel cadmium battery. So if stressed, level 2 thermal runaway, there are so many in news you can hear of the blast of the batteries or batteries catching fire, then degrades at high voltages and high temperature. Shipping is in large quantities requires transportation clearance. So these are the disadvantages of lithium ion batteries. So with this we have discussed the section B questions, and in next lecture we will discuss the section C questions, and that will be in part 3 lecture series. Jai Hind, thank you.